Hi, welcome to Mathematics with Tom. I am Tom. And today we are going to check the solution to a system of differential equations. And in our last video, we rewrote the differential equation using the matrix form. And we found our solution. We wrote that as a linear combination. So let's just make sure we have this down. This is the matrix equation here. And our solution over here, this is written as a linear combination. Okay, what we're going to do is check our solution. So check. Well, let's take the derivative. I'm going to start with a linear combination, and let's find the derivative of y. Well, you can't take a derivative of a vector that's just constant, so that doesn't matter. So the derivative is only affected by e to the t. That's e to the t, so that's c1 e to the t times the vector of 1, negative 3. Plus, and in this next component of our, or the next term in our linear combination, it's e to the 5t that is going to be affected by a derivative. So this is plus 5 c2 e to the 5t times the vector of 1, 1. That is if we take the derivative of y. Now, the next part of this says we're going to apply the matrix. We're going to apply the matrix times y. So the matrix is 4, 1, 3, 2. And we're going to apply that matrix. I'm going to put this in big, huge parentheses to y. Well, y is c1 e to the t times the vector of 1 minus 3 plus c2 e to the 5t times the vector of 1, 1. And we can distribute. We're going to distribute our matrix, if you will. And when we distribute it, we get this. Now when I distribute, I'm going to use some arrows here for explanation. When I distribute this matrix through the c1 e to the t, that's just a scalar, so that doesn't affect our matrix times the vector. So really what we're left with is we're left with a c1 e to the t times the matrix of 4, 3, 1, 2 times the vector of 1, negative 3. Plus, then we're going to pick up a c2 e to the 5 times t times the matrix of 4, 3, 1, 2 times the vector of 1, 1. Okay, well, let's continue with that. So this is equal to c1 e to the t. Now, notice this. If I take a 4 times 1, I get 4. I subtract 3, that's going to be 1. And then if I take 3 times 1, I get 3. 3 minus 6 is going to be a minus 3. Plus, I have a c2 e to the 5t. And let's do this again. So now I take the 4 times 1, that's 4. 4 plus 1 more is 5. 3 plus 1, or 3 times 1 plus a 2 times 1, that's another 5. Well, right now, our solutions differ a little bit, but let's rewrite it one more time. I'm going to write it this way. I'm going to write this as c1 e to the t times 1, negative 3 plus, now I can factor a 5, a scalar, a multiple of 5, out of that second vector. So this is plus 5 c2 e to the 5t times the vector of 1, 1. And there it is. Notice that our solutions match on both sides. Now, something amazing has just happened right here. Look at what we did. We took, for example, we took a matrix times a vector, 1, 1. And what did we get when we finished that? You might say, well, we got 5, 5. No, that's the simple answer, but the insightful answer is this. what we got is we got 1, 1. We got the same vector times some scalar. And what was that scalar? The scalar is 5. And not only that, but that scalar is the same scalar to which the exponential function is being raised. Now, is that true in the first one? As a matter of fact, it is. It's just we don't see it because it's 1, for example. When I take the matrix 4 times the vector 1, -3, well, what do I get out? I get out the same vector that I put in times 1. But remember, 1 is also the same number to which the exponential function is being raised. When you have that, this phenomenon, these are called eigenvectors. These are called eigenvectors. Well, actually, that's not the eigenvector. Let me write it over here. Eigenvectors there, and our eigenvalues are the exponent and the multiplier. Okay, and what this means is that really we took some matrix. In this case, it was the matrix 4, 3, 1, 2. That's by columns. We took it and we multiplied it by some vector. I'm going to call it x, but in this is the vector y, capital Y. And what did I get? I got some scalar times the original vector that I started with. This is the insight into finding eigenvalues and eigenvectors, and that is how we are going to be solving systems of differential equations moving forward. I hope that helps, and thanks for watching.